George, just thank you again for sponsoring this series. It's a spectacular series, really, really interesting speakers. And I'm sure that our audience will not be disappointed by tonight's speaker. I've seen Javier gives talks several times, many times, and I've enjoyed each time. So I'm Alex Wolf. I'm Dean of the Baskin School of Engineering. Baskin Engineering, we believe that engineering should serve society by addressing complex real-world challenges through innovation, collaboration, and a deep sense of responsibility. One expression of that work is the work we're doing to find solutions in the time of a changing climate. And this spans many areas from green computing to rare event prediction, smart power systems, sustainable farming through agro-technologies, many other areas. It also involves educating our students and giving them hope by showing how they as engineers can be part of the solution. It also emerges in communities, particularly those communities most vulnerable to the impacts of a changing climate. Assistant Professor Javier González-Rocha's work exemplifies this mission. Javier grew up in Watsonville and developed a passion for aerospace engineering. Javier's research centers on aerial robotic systems. This technology measures wind, turbulence, air composition, and complements land-based monitoring systems, all with an effort to be as accessible as possible, low cost, mobile, easy to deploy. What makes this work particularly compelling is how these advanced engineering tools are applied to problems of urgent societal importance. He understands how air quality and atmospheric processes impact human health, the environment, and particularly vulnerable communities. Though Javier has a BS and MS in mechanical engineering, has a PhD in aerospace engineering from Virginia Tech, and he did a postdoc in aerospace engineering, I guess, at UC Riverside. So tonight, Javier is going to illuminate how pollutants and climate-related emissions move through the atmosphere. Whether we're talking about wildfire smoke or methane emissions from dairy farms or oil and gas operations. These kinds of pollutants are extremely dangerous and yet almost invisible. Their impacts are also almost invisible. And the people they affect, frankly, tend to be invisible. So Javier's work is trying to shed a light on these pollutants and their effects on the communities. He will discuss the mathematics behind his technical approach, but not too much mathematics, I hope. To discovering these hidden pollutants in our world and how he applies the technology to real-world environmental problems right in our own backyard. This work reflects Baskin Engineering's ethos, demonstrates how technical innovation, when paired with collaboration and purpose, can empower communities and support climate resilience. So, Javier, please.
All right. Can everyone hear me? Yeah. Well, thank you for being here. It's very exciting to be with you and share the work that we've been doing at UC Santa Cruz. So the title of this presentation is Sensing the Unseen, How Drones and Ground Sensors Reveal the Hidden Air Quality Impacts of Climate Change. And so first, I want to talk about why does atmospheric sensing matter, specifically wind, right? And so here I brought a few examples. And so it turns out that wind sensing is really important for real-time decision-making. So when we think about realizing precision agriculture. So one application is targeted spraying, guided by wind conditions. Why does this matter? Because we want to spray during the times where the transport from the machine to the plant can be most effective, so that the majority of the chemical gets delivered to the plant. And then we have minimal drift, and therefore we impact communities very minimally. Then the other example is tracking hazardous plumes. And just about a year ago, we were dealing with a very serious plume, and this is the plume from the Moss Landing fire. So knowing what the winds are doing is really critical to understanding how this plume will behave, right? And how to give people instructions on how to protect themselves. And then the big one as well is wildfires, right? So with climate change, where there's more wildfires, and these wildfires produce a lot of smoke. When I actually was coming back from Virginia Tech, we had a very big fire, the CCU fire. So everyone in the room was impacted by that. So wind affects all of this. And so if we can reliably understand how wind patterns are changing with regards to both space and time, then we can respond to it in a much better way. So let me tell you, this is going to be the story that I'm going to tell you first. So first we're going to talk about how we can use aerial robotic systems to measure wind. Then I'll talk about how we've extended these innovations to measure other things, and in particular methane. And so we'll talk about how we're using these innovations to provide alternative methods for estimating emissions from dairy farms in the state of California. And then I'll share how the insight developed doing this work has helped shape the work that we've been doing in the past year or two around preparedness and resilience for wildfires. So let's talk about winds. So winds we measured in various ways. So there's two types of sensing that we employ when we measure wind. So we have in situ sampling or in situ sensors, and then we have remote sensing or remote sensors. So the in situ sensor is what you see on the left, and basically in situ means local. So what the equipment is doing is that it's providing a local measurement of wind velocity. Now, what are the advantages of these measurements? Well, the advantages is that these instruments are usually very high resolution in time, right? Now, these sensors can cost anywhere from $400 to $10,000 and sometimes even more expensive, right? But I'm just giving you the range to keep in mind. Now, if you want to understand how wind is changing with respect to space, well, one sensor is not enough. So then we need many more in situ sensors, and then we have to think about that cost of scaling up. Right? And that's where that's sort of kind of what motivated the development of the other technology. So remote sensing is basically we're measuring from a distance, right? And so here are these two technologies, so SODAR and LIDAR. Maybe you have heard of LIDAR, might be more familiar, but SODAR stands for sounding and ranging. So what happens is this SODAR is basically an array of speakers. It chirps into the atmosphere, and then it listens to the scatterback that comes back from the turbulence in the atmosphere, and it uses the Doppler effect to triangulate what is the wind velocity. The LiDAR is working on the same principle. The only difference is that now what we're emitting is a light signal, not a sound signal, right? And so a SODAR you can find in the market from anywhere for about $41,000 to $170,000, and a LiDAR about $200K. Now, these sensors give you measurements at about every 10, 20 meters. So it's great in terms of getting higher spatial resolution, but the problem is that these measurements are averaged. So all of us. So on the other side, on the counter is you get less temporal resolution, right? So nothing a perfect split. So we've been exploring how can we use aerial robotic systems not to replace these technologies, but how to complement them. Now, what's the motivation? Well, these systems are actually quite mobile, economic, and easy to operate, and they're very maneuverable. My PhD dissertation came out of a drone that cost about $500. So any drones that range anywhere from $300 to $15,000 can give us measurements, right? And so that's the power behind this work. Now, when we're thinking about wind sensing derived from drones, there are two camps, or there are two methods, and then folks the very early folks that started to see the opportunity in aerial robotics sensing for atmospheric, for collecting data in the atmosphere, they saw the drone as a sensor carrier. So they were just simply thinking, how do I mount a sensor that measures wind, so that's what we call a sonic anemometer, on an aircraft, and so therefore I can drive or fly the aircraft to where I want to collect the wind measurement, and then do some science with that. Now, what are the drawbacks of this method? Well, one is that you're carrying a sensor that has weight, and so you're depleting your flight time, so you have less time to fly. The other thing is that you need to take into account the motion of the aircraft, and also the propellers might be disturbing the flow that you're interested in measuring, right? On the other hand, we have this idea of what if we convert the sensor itself into the wind sensor? What a novel idea. And so folks that started looking at this idea were first mapping a relationship between the attitude of the drone and the wind speed. So the assumption there is that wind doesn't change with time, right? And my work has explored mathematical schemes for relaxing the assumption that the wind doesn't change, and see what happens when we use higher fidelity models. So these are the mathematics. So we've developed 3 models. So the first model is a kinematic particle, the second model is a dynamic particle, and the third model is a rigid body model. So in the first model, I'll just summarize. So we treat the aircraft as a kinematic particle. So we don't take into consideration any masses, right? And in the second model, we still have a particle, but now the particle has mass. And the effect of the wind both affects the kinematics and the dynamics. And we also have the effect of forces, both aerodynamic forces and control forces. But everything is still translational. In the rigid body model, we are now taking into account rotational dynamics. So there's this level of complexity that's increasing. And then the question that we ask is, if we consider the vehicle as a low-pass sensor, will the accuracy of the wind estimate increase with the model's fidelity? In other words, is it worthwhile to use a higher fidelity model to measure wind versus a lower fidelity model, like a kinematic model? And so I'll show you how do we actually characterize the most sophisticated model. So this is the rigid body model. So what we do is we actually flight these systems and we excite these systems. And so we start from very slow motion to really fast motion. And what we want to do is we essentially want to find the model that describes the relationship between the input and the output. Once we have found that model, we validate that model. And we do this in 2 steps. In the first step, we take the data and we identify the model structure. So the model structure is essentially telling us which variables are important, more important, and which variables are less important. We disregard the variables that are less important, and we keep the variables that are most important. So this is the process of model structure determination. And then once we have our model, we do what's called output parameter estimation. And what we do is, taking our initial guess, we then use an optimization scheme to find what are the values of A and B. So we're basically now learning what are the actual, refining the values of A and B. And so here, we're taking our model structure, we're taking the data. Now, when we do this, I want to make it clear, rotorcraft are really fun to work with, and one of the things is that we can decouple the dynamics. So we actually do this for different modes. So the modes that we consider are the punch mode. So this is motion up and down. We have the yaw mode, which is spinning in place. Then we have the roll mode, and we have the pitch mode. Once we've constructed these models, then we do validation in real-world environment, right? So here we're showing the aircraft is flying, and so we fly next to a weather tower that's recording wind. And so one of the questions that I want to ask you is, if you were to hedge a bet, on which model would you bet? The kinematic particle model, the point mass model, or the rigid body model? Which one do you think is going to perform the best? The one with the more meth, that's the right answer. So I'm showing you two plots, right? So the black signal is our control. So that's what we got from the ground, from the tower sensor. The green signal is the estimate from the kinematic particle. The blue is the estimate from the dynamic particle, and the red is the estimate from the rigid body model. At the bottom, I'm plotting the root mean square error for each one of the signals. And so in the first flight, we flew for about 160 seconds. And you can see the winds went from 2 to about getting close to 6 meters. And through that change, the model with the more math did better, right? And then we had another case where the winds were oscillating about 4 meters per second, and we see the same story, right? Now, what I didn't tell you was that the intermediate model required about 140 wind tunnel experiments, which is a lot of work, right? And it's the one that performed the least best, right? So all in all, across all of these models, the rigid body model, the most sophisticated model, is actually easier to characterize using modern data-driven approaches. So that's the good news. Now, when doing this work, we're working with scientists, and then the question the scientist was, this is phenomenal, can you measure the wind while ascending? So I saw one problem and immediately got the next one. And so we went to work, and so we were able to prove that the scheme is not only effective for measuring winds while hovering, but also ascending. And let me show you results from some validation experiments. Now, the data is a little bit messy, so let me walk you through it. So we're basically comparing estimates from the drone ascending at different rates to measurements from two sensors. So the first sensor at the top with the green marker, that's a SODAR, and that's what we're calling the long-range SODAR, or the LR SODAR. Then the other SODAR is the short-range SODAR, and we're demarking it by a red marker. So you can see we did flights, so we started quite early. So at the very start, if you look at the very start and you go towards the end, you can see the comparison between these two measurements, right, which are the ground truth. And the circular markers that you see, so the orange, the purple, the magenta, the orange, these are all estimates that we're getting from the drone. So the top panel is wind speed, the bottom panel is wind direction. And what do you see? You see that the drone actually did a great job filling in the gaps, right? So we did quite well estimating wind velocity. Now, experimental science is quite hard, and there are so many unexpected things. So when we actually did these experiments, the thing that we found out is that the noise from the drone actually corrupts the sensors from the measurements from the SODAR. And that's why you don't see a one-to-one comparison, and we had to throw that data away. But still, looking at the measurements from before and after, you can see that the measurements from the drone fall right within the air. It's within the air that we see between the other two sensors. And all of these sensors were side by side while measuring. So what are some of the things that we can summarize about model-based wind estimation using aerial robotic systems, or UAS on crewed aircraft systems? We've shown that we can transform drone motion into reliable physics-based wind measurements. So hopefully I've convinced you with the data that I've shown you, and that the model-based UAS wind estimation enables accurate wind sensing, both hovering and ascending. And now I want to show you how we can take these measurements to understand transport, to address some of the biggest challenges in the state of California. Now, how many of you are familiar with methane here in the room? Okay, so the majority of you. So let's talk a little bit about methane. So but I think that's really important because it's a very potent greenhouse gas, right? So it's a second most potent greenhouse gas after CO2. And it's estimated, and there's still some debate about it, but the dairy farms produce about 50% of the emissions in the state. And so the inventory measurements that we have now have a big error bar. And I'll explain to you where that error bar comes from. So to do this,
To improve these measurements, we need to have higher resolution observations of winds, turbulence, and air composition within the planetary boundary layer. At least that's the approach that we're taking. And we've been exploring how we can combine measurements collected from satellite, aircraft, with rotorcraft measurements to get a better estimation of what are the emissions that are coming from these dairy farms. Now, I think most everyone in the room has an understanding of how much dairy farm activity we have in the state. But if you don't, here in this map, what I'm showing you is every dot is a dairy farm. So we have a lot in the state, specifically in the Central Valley and in the North Bay near Santa Rosa. And then there used to be a lot more in LA many years. But we can see that the majority right now it's in the Central Valley. And maybe before I continue, let me tell you where the uncertainty comes from in our estimates. So the way that we estimate emissions right now is that we assign an emission factor to every cow. So you need to know how many cows are in every farm to then multiply times this emission factor. And so you need large-scale cooperation, even assuming that this emission factor is correct, to get reliable estimates. And so this is why there's such a big error bar. So this is work that we've conducted with our colleagues at UC Riverside, so Sihan Su, Don Collins, and Francesca Hopkins. And so we've been exploring methods to use aero-robotic systems. And in our first approach to solve this problem, what we did was we took an air core. So what is the air core? So the air core is just a very long piece of tubing that's connected to a pump. And then we just fly through the atmosphere. And we collect an air sample. We essentially fill up the tube with air. We come down, and then we connect it to what's called a cavity ring-down spectrometer. And then we sample that air, and then we look at the concentrations. And so the reason why we call it an air core, it's very analogous to what happens in the North Pole, where you take a core of the ice. So that's an ice core. So this is air. So we're doing a similar thing, but in the lower atmosphere. So this is why we call it the air core. And so the idea is to fly, so you have the emission source, so fly up and down, collect wind measurements, and collect concentration measurements, and use that to estimate emissions. So here's just the picture to give you the scale of the drone and the air core in flight. In the middle, I'm showing you one of the dairy farms where we did measurements. I think most of you have already seen one of these dairy farms, but if you haven't, this is the scale. So you have something that's 800 meters by 945 meters. It's quite large. And we're flying just under little of 2 kilometers away from these dairy farms. These plumes are gigantic. And the idea is to see if we can collect measurements. So here are some of the results. So on the first panel, what I'm showing you is wind speed. So the blue is what we collect ascending, and the red is what we collect descending. In the middle panel, we have wind direction. And on the third panel, what we have is the actual enhancement that we measured along the way. So we actually flew through what looks like 2 plumes going up, right? And so these plumes mix. These flights took place early in the morning, relatively early. This is winter time in January, where it's really cold in the Central Valley. So we actually were able to capture the plume fairly low. Now, we did a flight much later and see the difference in the profile, right? So we see that the plume was a lot more dispersed, or we were capturing concentrations much higher. Now, this is very powerful because without doing this with an aircraft, our measurement is just what we have at the surface. We can only know what the concentrations are at the surface. So now with this technology is essentially we can not only understand what the winds are doing, but also understand how is it that the winds are affecting the dynamics of the plume, so that we can capture most of the concentrations. Now, once we have the concentrations, our job is not done. Concentrations are not just good enough. We want to know an emission rate. So what we do is we take a dispersion model. So the dispersion model that we use is a Gaussian plume model. And this model basically tells us how the plume is dispersing horizontally and how it's dispersing vertically away from an area source. So now we can take our measurements from the aircraft. So these are, we took about 12 measurements, so average every 10 meters. And then we can go from measurements to an emission rate. And so two things that are very critical is, in this case, we obviously knew where the dairy farm was, but we did a first assessment to see if we can take the wind information and if we can take the concentration information to try and find the source. And so we developed this footprint. Not the most accurate, but at least we were super happy to see that if we had no idea where the farm was, at least combining this data, our farm actually ended up being within our hotspot, or what the model was telling us where the emissions were likely coming from. So this is good for detection. And then we were actually able to get emission estimates, and we compare these emission estimates to bottom-up estimates. So these bottom-up estimates, again, get generated by counting how many cows you have, and you multiply them times the emission factor. So those are the bottom-up estimates, and then you have the mass balance estimates. So the bottom mass, you essentially have to fly, do a curtain path downwind of the dairy farm, and then upwind of the dairy farm, and figure out what was the mass balance. And that gave us the highest emission, but also the largest error bars. So in conclusion from this work, one of the things that I want you to take away with is that by combining this technology of drones, the air core sensing capability, and dispersion models, we can get estimates that are somewhat consistent with the bottom-up estimates, but we have less uncertainty, which is very important for getting us to the point where we can take more decisive information. Now, these are work that has been done to quantify emissions at a facility scale. And so more recently, we've been doing work to look at sub-facility scale. Now, why does this matter? So in a dairy farm, so it's a picture again of a dairy farm. So it's estimated that within a dairy farm, about half of the emissions are actually coming from the manure lagoon system. And the state of California has invested about $150 million to mitigate these emissions. And the way that we're mitigating these emissions is by actually using anaerobic digesters, right? So that way we can capture the methane. And so the idea is that we use the methane as a renewable technology. But as this gets unfolded, there's been limited testing on these systems to see how reliable they are, right? The good news is that it's farmers are adapting them at a faster rate as we go into time. The bad news is that there are some concerns about the emissions. So these are observations that have been collected from an aircraft. So NASA JPL does these operations. They fly this sensor. It's called the airburst sensor. And they basically look over these sources and they can see these plumes. And so this is one of the digesters. So this was the first measurement, November 12, 2021. And it had a leak where they're estimating it's 281 kilograms per hour, plus or minus 102 kilograms per hour. Think about how much is that across a year, right? It's a lot. And then if you look at the next measurement of the same site, it's 218 plus or minus 69 kilograms per hour in September 16, 2022. Still quite a lot. And then more recently, in 2023, there was 72 kilograms plus minus 29 kilograms. And there is this question of, these emissions actually reduce, or is it a product of the micrometeorology? So if you see on the first plus on the left where we have high emissions, you have this sort of kind of splatter of the plume. That means that the wind conditions are low, so you get the plume meandering everywhere. On the right, you see a more defined plume, and so the wind conditions were higher. So we've been trying to do work with aircraft, and we're taking our applied mathematics students, and we're getting them to get their hands a little bit dirty and work with some of these aircraft, but we've been developing methods to collect measurements. And so we've developed a very low cost and actually system to capture some time integrated observations down of these facilities. And we've actually shown that it's possible to understand, to better capture these plumes that are coming from these facilities. And so here are these two measurements that were conducted 2024 downwind of one of these facilities. And so what you see is 10-minute time average measurements at different heights. And I'm showing you the methane concentrations. And one of the things that we see is that around 5 to 6 p.m., we saw the plume height at about 40 meters. And then as we get closer to 7, 8 p.m., we see the plume around 20 meters. And as we look at this data, we see this pattern repeat over and over again, which is good for helping us estimate the emission. So what are the big takeaways? Is that we can use these technologies not only to understand emissions at facility scale, but also at sub-facility scale. Now, why does this matter? Is because we can use these measurements to see how effective our solutions are being. And if there are problems where we can be better, identify those and then correct them. And then again, assess whether our corrections were actually effective, right? And we can do this by combining both the wind measurement, the methane measurement, and the dispersion modeling. Now, why does this matter beyond methane? Well, other pollutants that transport in the atmosphere follow a similar behavior. So we've been taking the things that we've learned from plume transport processes governing methane transport to look at other pollutants, specifically looking at wildfire smoke dispersion and exposure from other pollutants. So there's been, Alex mentioned it, but there's been a lot more literature that's been coming out about the impacts that climate change is having on farm workers. And in fact, the number of farm workers that have died in the last 5 years has increased dramatically. And this is due both to exposure to pollution and exposure to higher temperatures while working, right? And well, and so here I'm showing this article that details, that sort of highlights the research. But one of the things that caught my attention in this article was this picture that they had where they have people laboring. And what you see at top, you see a layer of pollution, right? And so the question that we had was, what if we could track this layer of pollution across the day and see if it ends up coming down? And if it comes down, when is it that it comes down, and how is it that it's affecting people? So we worked with a team of students. This was part of their capstone, and so we augmented a drone with a low-cost particulate matter sensor. And we've been able to develop this technology to complement that with temperature, pressure, and relative humidity to understand how is it that pollution is changing. And, oh, I went the wrong way. Now, let me tell you why this can make a big impact, especially in agricultural settings. So here I'm showing you, if you're not familiar, this is the Pájaro Valley, so it's on the southern part of the Santa Cruz County. So this is just south of UC Santa Cruz. And what we see is that, as it's reported in the literature, we see some of the same patterns. So there's a lot of impact, there's a lot of burden on these agricultural communities. So Watsonville, I think most everyone's familiar with Watsonville, so we grow strawberries. And what do you see then when you look at the county is that you see the orange. And so that means a number of things. That means that folks there have to deal with more exposure. They have more sensitive populations, so these are populations that are vulnerable to air pollution. And then there are socioeconomic factors. So about the exposures, let me just provide you a picture of what's going on. So we have diesel particulate matter. So that's, we have an index. So this is rated based off an index that goes from 0 to 100. So you're in 100, that means that there's 99 communities that are better than you. So, so we're not the worst, but it's still significant, this diesel particulate matter. Then there's contribution from traffic, so that the index 64. Pesticides is a big one, it's 100. Drinking water, and lead from housing. These are all compounding effects, right? So this is what creates our baseline. Then we have an index of 58 with people with asthma, low birth weight, 38, and cardiovascular disease, 42, which are definitely not small numbers. Socioeconomic factors, access to education, 96, so that's something that we're working on. Linguistic isolation, poverty, unemployment, housing burden, right? So when these pollution events happen, they have a disproportionate impact on these communities. And so here we look at the CCU fire, right? So what did we experience during the CCU fire? Well, we all got engulfed with lots of smoke, right? And many people were actually affected by the actual fire, but the impacts from smoke can be significant. So here I'm showing you, this is what the regulatory monitor at Santa Cruz recorded. So this is, the fire happened in August. You see this big spike. So we go up to nearly 400 micrograms per meter cube. And then what you see here is this dashed line that I'm showing. It's actually what the 24-hour federal standard. So we exceeded that by 40 times. And see if, and while this all happened, people continued working, right? Then the following month, September, air quality got better, but still twice as bad. And then it took some time until we got finally through that threshold. Now, when you look at the infrastructure for sensing air quality, we see that there's a big gap, right? And there is a negative correlation, actually, where we have high burdens is where we have the fewest monitors. So the map on the left is the one that is showing you the burdens. The map in the center is showing you the state-operated regulatory monitors. So you see that there's a discrepancy between where these are. Now, as a response to the smoke impacts from this fire, at least it's a conjecture from the trends that I've seen from when the purple air monitors went up, we got lots of them in Santa Cruz County after the fire. And that's because people understand the importance of air quality. But what do we see? There is still a very large gap in the agriculture community of Pajaro Valley. There's not a lot monitors. So we've gone to work, and so we've established partnerships with local communities. So we wanted to hear from the people themselves how they were being affected by air quality and what they thought were meaningful technological solutions, right, that we could contribute to help them in the process of getting better, of being better prepared to build fire resilience. So we work with, for organization Regeneración, Center for the Community Advocacy, and then the Community Action Board in Casa de la Cultura. So we had these listening sessions where we heard from the community what were their concerns. Then we started deploying some of these monitors, and some of the exciting news were that where there were some questions as to maybe the community wouldn't be ready to adopt technology, they actually helped us install the majority of the sensors. So it wasn't that they were like, yeah, sure, you can come and install the monitor, but there was like, how can I help install a monitor? And so here we have a gentleman, so one of our community collaborators, he's actually going peer-to-peer and talking to them about this project and engaging them and helping me install these monitors. So this is the difference that we've made in just over, I think, about 8 months, right? So this is what we had before, and this is what we have after, right? And we're still building on this. Now, the purple air monitor is what we have over there. And now, why did we work with the purple air monitor? Well, the purple air monitor, it's an off-the-shelf color. It's off-the-shelf center, and what we really liked about it is that it gives you a light. Because what we were thinking about is how do we get data to the people in the quickest way? And for a lot of these people, just having a monitor that changes light, depending on the air quality, is the most accessible way for them to know what the air quality is. So we've deployed these monitors to look at air quality, and we've been especially interested in thinking about how does air quality change as we have prescribed fires happen? And we recognize that prescribed fires are a very important tool that we need to use to reduce the risk. And so what we're thinking is, how do we use these sensing technologies to make prescribed fires more sustainable so that we can increase the number of prescribed fires that we're having without severely impacting communities, right? And so here I'm showing you the map of, this is in the month of October, all the prescribed fires that happen in a region in our air basin. And this fire is the most recent fire that we had in October. This is in the Wilder Ranch in UC Santa Cruz. So this is our sensing network. So on the left, I'm showing a number of graphs. So the first graph is showing you the hourly PM2.5 concentration that was recorded. The prescribed fires actually took place on October 6th. So down in the community, we actually saw the impacts on the 7th in the early morning. And this is how things look like. So this is the Pajaro Valley. This is the video. Look at the colors. Everything's good. Then things get bad, a little bit better, and then worse, and then they get better again. Now, what have we learned from this data is that The distance between the prescribed fire and when people felt the impacts in the valley were far apart enough where there's a disassociation between the prescribed fire and then the impact. So people aren't thinking about the response, right? And in fact, the highest concentration was recorded at 9 a.m. On average, farm workers begin to work at 6 a.m. So that means that they were already working 3 hours when the air quality was the worst. So if we made this data accessible both to farm workers and employers and everyone else, then we can actually think about things that we can do to shift this change. Now, the measurement, the sensors itself, it'd be lovely to place them everywhere where we can, but that's always not a choice or not a possibility. So what we've done is we've started to work with different interpolation techniques to try and interpolate what are the concentrations in places where there aren't any monitors. And this is looking at 9 a.m. You can see, based on the work that we've done, that the predictions show that the air quality was impacted at 9 a.m. throughout the entire valley. Now, when we look at the reliance of these measurements, everywhere where you see yellow, that means that there's lower confidence in the measurement. Now, why is that? So we have these gaps. Well, it's because we don't have many sensors there. So some of the limitations that we're running with these sensors is that they're about $300 per unit, and each unit requires Wi-Fi, and they have a fixed hardware and software. So there's not much that we can do to work with these sensors beyond what they can already contribute off the shelf. And that's where our students have come to save the day. So we've got this project, so it's the AirWise project, and so it's extending community air quality monitoring beyond off-the-shelf sensors. So this is a project with Katia Braxa, Boyang, and myself, and so what we're thinking about is how do we integrate IoT technology, Internet of Things technology, like these monitors, with drone measurements and satellite measurements to generate products that can help us be more effective developing readiness training, gives us data analytics tools, and overall we can just build higher resilience. Julius is here, so he's one of our undergraduate researchers, so if you have any questions, you're welcome to ask him questions. But together we've been developing this new sensor. So the sensor is not as pretty as the purple air sensor, but it can do a little bit more. So one of the main features of these sensors is that they don't require Wi-Fi access. So we're using radio communication to relay data from sensor to sensor. So this means that we can get away from the city. We're also able to not only sample PM 2.5, temperature and pressure, humidity, but we can add other sensors. So for example, if we're in an agricultural community, there might be concerns about methane production from some of the agricultural practices. So we can be looking both for PM 2.5 and also methane simultaneously so that we can better understand the correlation between these two events. Now, these sensors are based on the LoRa infrastructure. So the LoRa infrastructure, so here you think about bandwidth and range. Although these sensors have lower bandwidth, so it means we can share maybe less data, but they have a wider range. So they have a wider reach, and so they help us overcome both the barriers that we have with Wi-Fi and cellular data. And the way that it works is that all of these sensors, they're relaying data to each other, and then there's one sensor that is the sensor and the router, and there's just that one sensor that needs to be connected to Wi-Fi, and that is the sensor that uploads the data. And while we're doing that, we're also continuing to think about the physics of transport. And so we're working on the next generation of aircraft. And so these are the aircraft that we want aircraft not only to be able to sense both wind speed and particulate in the atmosphere, but we want the aircraft itself to maneuver based on these measurements. So that way we can remove the human in the loop. And so here I have some examples of transport under strong winds and calm winds. Right? So if the aircraft can sense that the winds are strong, then it knows to look for particulate matter down to the surface. And if it knows that the winds are calm, it knows to go higher to look for the plume. So you'll stick tuned, you'll learn more about that. But now just to close the talk, so here are some of the key takeaways. So we make invisible air pollution visible by linking emissions, transport, and exposure, right? And we saw that from the work that we started developing the robotic systems to measure wind and how we apply that for methane transport, and now looking at work with regards to exposure from wildfires and prescribed fires. We've integrated drone and ground sensing and shown that this can enable scalable and interpretable measurements across hard-to-monitor environments. So many places where we operate these sensors are not accessible. And so really, this technology makes it easier. And then these tools reveal that wildfires and prescribed fires and methane impacts at community scale, which are still to this day hard to achieve. And so by translating measurements into actionable insights, we support community scale decision-making and climate resilience. And of course, I also want to thank our students. Everything that I've shown you is thanks to our students. So we've been so lucky to be able to engage so many bright students at UCSC. So we have many people that have contributed in their lab. And also are grateful with many collaborations within Basque Engineering with many colleagues. So we've been doing work with the Center for Coastal Climate Resilience. We've been supported by Citrus programs, so Citrus and the Banana Institute, the Center of Agroecology, so we're now deploying some of these sensors at the farm. The Center for Reimagining Leadership, and our community partners, Regeneración, Center for Community and Advocacy, and Casa de la Cultura, and the Community Action Board. So with that, thank you, and let's have a conversation about. Thank you.
I'm wired. Thank you. Thank you, Javier. We're going to just have a little conversation here, but we'd also like to have you involved in this conversation. So I encourage you to think about some questions or comments, reflections you might have on this work, and even more broadly. But I'll get us started a bit. By the way, I have an acronym for your lab, particularly with respect to the work on methane. Yeah. Flying Air Reasoning Technology.
Love it.
Got it? Okay.
I love it.
Yeah. That brilliant idea came to me. That's why I'm a dean.
Can someone write it down? One of my students, can you write that down? Can you say it again?
Flying Air Reasoning Technology.
What's your logo going to be?
Oh, yeah, there we go. I'll leave that to the arts division. Okay, so Javier, you have an interesting background personally with respect to some of these issues. I wonder if you could share a little bit about that.
Yeah, of course. Hopefully I don't lose my microphone, but just borrowing a little bit from mathematics. So, solutions depend on their initial conditions, right? And so I think for me, I'm very fortunate because I was born in Watsonville. My parents were migrant farm workers. I remember the space shuttle program was still going. It was still very actively going on, and I just loved seeing us launch into space. And that's what got me excited about aerospace engineering. And I remember I wanted a computer, and my parents, they said, we would love you, but we can't afford it. But if you come and work with us, we'll let you keep the money and you can buy your computer. So I remember I bought a big compact tower back in the day. But even having that experience, I got to learn about what people went through. So there are a number of things. One is the tremendous opportunity of being in this country and the tremendous value of education. Everyone I work with were like, take advantage of your education. And that's kind of what got me committed to go all the way to pursuing a PhD. But now I say, I went to this PhD and did this great work. Along the way, I also discovered this passion for working engineering and science, right? Working together to tackle problems. And so if you combine that with my own personal experience, most academics don't get to come back to their communities. And so I don't take that opportunity for granted. And so, while it'd be easy to say, oh, I'll do it after I get tenure, I think for me it's, I wanted to make sure that I live true to my values and that, from day one here, understanding that this requires time to build, to start focusing on things that matter the most. And this is sort of the reflection of why I do the work that I do, right? Otherwise, it would lose its soul in some way, like if we didn't involve the community or felt like it had that commitment to community and society.
Yeah, that's wonderful. Yeah, there are a lot of faculty, I think, who are, particularly at UC Santa Cruz, I mean, it's part of the ethos of UC Santa Cruz, is to engage with communities. But many of faculty sort of fall into a trap, or they find difficulties in actually meaningfully engaging with communities. How do you think you were able to overcome some barriers and be able to actually, I guess, gain trust with the communities?
Yeah, I think the way that I think about it is, as we start to engage with communities, we very much work, the way it works is usually, well, you need funds to do a lot of this work, and you usually write a grant, and then once you get the money, you do the work, and once the grant is done, the work is done. That won't work for building trust, right? So we really need to show up, and we really think about how do we bring both knowledge, technology, and just anything that we can provide as a university that's going to be long-standing. Once the university can see that we're bringing value that is going to survive the time scale of months and just a couple of years, I think they're willing to commit. Because then they see the benefit. And especially these communities, most of them, when I talk to them, they're willing to tolerate things for themselves. But when they get sort of more activated is when they learn what the impact is on their children. And so if you can make the connection as to, this is not only how it's impacting you, but it's also how it's limiting the generations, the development of the future generations, then all of a sudden they enlist to want to be part of the solution. When we did some of the focus groups, one of the questions that I asked was, how many of you want to be involved in decision-making or leadership? Most everyone raised their hand for that same reason, right? So I think that has been important. So as long as we come together and from the very beginning establish those values that this is not a shared responsibility for the length of a project, but this is shared responsibility for many years to come. And I think that's where the dynamics begin to change. But yeah. So
maybe apologize for focusing on some of these issues, but I kind of trust you do the math right.
Yeah.
But bringing it to actual, utility is something that I think is really fascinating. And I think it's also fascinating that an engineering faculty person would be doing that. It's not usually associated with people who are working in STEM.
Right.
It's usually focused on people who are working in the humanities or in the arts that think that, that's where that passion comes from.
Yeah.
But I'm seeing it here in an engineering faculty member. So you're talking about the communities, and they tend to be the farm workers, but there's another constituency, at least one other constituency there, which are the farm owners,
or the growers,
the grower, right.
Yeah.
So how is that interaction working with them, and what do they think about your interaction with the farm workers?
Yeah, so that's been a conversation that we've been developing, right? And so there's so much power in data. So if we can demonstrate that the data is there for working on things, I think most of the stakeholders want to do right by these circumstances. And so once we generate the data, we can think about ways in which we can all learn from the data and improve our well-being for everyone, right? So for an employer is just convincing them that, if they have a healthy workforce, they have to be less worried about, will we be able to harvest, everything that's ripening, right, or that's becoming ripe.
Productivity.
Yeah, productivity, right? So balancing those things and becoming sort of more thinking more about long range than thinking about short range, which many of them already beginning to do that. And the hardest part in my experience is just getting the conversation started. Once you get the conversation started, there feels like at the beginning there's some resistance, but eventually once folks get a sense that everyone that's participating in this has genuine interest, you get some nice convergence.
Yeah.
Because everyone's solution oriented.
Because obviously this is costing money.
Yeah.
I mean, these devices aren't free.
Right.
Is there any incentive for the farm owners to
So
actually pay for some of this?
So some of the things that we're talking about are actually also having effects on the plant. So it's been already well documented that, for example, smoke or ash that lands on a plot has lowers the productivity, the yield of the crop. So that would be one incentive. Another one in the valley, in the area, more broadly, also thinking about Salinas Valley. We have an ecosystem where it's both conventional growers with organic growers, right? And so it's also a value because it often happens that these things are transporting. So imagine there's a conventional grower that's applying pesticide. This thing drifts and it lands on a berry that's supposed to be organic. This strawberry then goes to the distributor and they do some inspection and say, hey, there's pesticides here. We can't accept your crop because this is supposed to be organic. So that has a financial cost. So I had friends that are growers who the distributor said, we can't accept this and we won't accept your fruit, what you produce for the next week, sort of as some disciplinary action. So that means that there's money being lost. So from that stand, they have plenty of incentive to want to monitor transport, to better understand how things are moving with the different with the different conditions.
Very interesting. So what about, you and your students go in there and you operate these drones, these flying sensors. You've got some stationary sensors, obviously. You're enhancing it with the flying sensors. That's also not quite sustainable, right?
Yeah.
So how are you thinking about getting the drones in the hands of the people who are living in these communities and getting them to operate and do the sensing?
Yeah, and part of that is developing the conversation of when is it ideal to have these systems, right? Or when is it ideal to deploy these systems? So I just got an email today, someone from the San Lorenzo Valley saying, hey, we have a horrible inversion. Can we fly some of these sensors to look at the pollution, right? So just understanding when is it that we can deploy them. That's one thing. There also, we had the Moss Landing event, and there was these questions of what was in the plume. So although it's hard for these systems to fly all the time, having something readily available to fly and be able to measure something, that's of tremendous value, because otherwise...
So sort of a quick response team sort of thing.
Yeah.
So for those who don't recall what the Moss Landing incident was, it was the fire at the power station. It was these storage batteries for electric storage batteries that are highly volatile, and they caught fire yet again and put a lot of very toxic material into the air.
Yeah, exactly. So, and I think about, if they're not, if it's not sustainable operating them all the time, how do we get them operating more sustainably, meaning or more consistently, right? Yeah. And one of the things that we're actually looking at, that's something that we've been through Citrus Aviation, we've been looking at advanced air mobility. And so advanced air mobility is essentially opening the sky to lower atmosphere operations, both of electrical vertical takeoff systems that can carry people, and then smaller people, sorry, not smaller people, it's packages, right, from point A to point B. And then how do we capitalize on these operations that are going to be happening? Because, I don't know, someone is ordering something on Amazon to collect wind information, to collect data about the environment. So a small anecdote, so we had a project in Bakersfield, and we were just driving around with sensors, and we found 5 leaks, gas leaks, just driving around these sensors. So the the utility company were like, boy, you're really putting us to work by finding these leaks, right? So now imagine if it's these aircraft that are flying to deliver a package that are equipped with a small sensor so that they can pick these signals and be able to say, hey, I'm sniffing something here, send something more reliable to double check.
Yeah.
Right? So the future is promising. I think there is a time where aerorobotic systems will be more sustainable, collecting atmospheric observations for all sorts of purposes.
It reminds me of postal workers, delivery people who actually were employed to do community policing, right? Because they're driving around, they can observe suspicious activity and can report on it.
Right.
And it's just this sort of taking advantage of
so we call it
that.
piggybacking,
Yeah.
It's like, how do we piggyback on existing operations?
So, it is still regulated space, right?
Yeah.
You are working with students.
Yeah.
How are the students trained or able or allowed to actually operate these drones in these areas?
Yeah, they actually become operators. So, and this is the great thing about the fact that we have Citrus on campus.
What is Citrus?
Sorry,
I know what Citrus is.
Yeah, but I don't remember the whole.
Center for Information Technology in the Interests of Society.
That's right. So they have a program where they provide training to the students, and so the students are supported to get their own license. So I try and recommend as many students through that program. The students that don't get selected through the program, we still fund them through the lab. So we use funds so that they can prepare for the exam. They take their Part 107 exam, and once they pass their Part 107, they're certified in the FAA's eye or in the government's eye to do flight operations. So in fact, these are students that are leading the operations, especially when we have multiple aircraft operating.
There were some pictures of the drones flying at what looked like an airport. Where was that?
Yeah, so this is a experiments that we did just over a year ago at Virginia Tech. So we've maintained some collaboration there, and so these are experiments that we did for a shared purpose. So they're interested in understanding how spores transport, and so I was interested in learning more about smoke transport. So we decided to do these nice, colorful experiments because we can visually see how transport is changing when it's cold versus when it's hot. Yeah.
Yes. By the way, any questions, please, or comments, anytime. There's one online, and then we have one here. So
Yes.
let's take our Zoom audience.
Yeah.
Let's take our
Yeah,
Zoom
okay.
audience first, and then we'll go here.
One of the questions from the Zoom audience was, what is the physical scale of wind motions that is the most important for pollutants? I.e., is the wind layered vertically and variable on a scale of centimeters, millimeters, or kilometers with regard to human impacts?
Yeah, that's a very good question. So it depends. So when we look at large fires or the smoke coming from large fires, so often when we have fires in the Sierras, folks in New York get our smoke, right? And so that's the synoptic scale. So that's many kilometers, right? But when we're thinking about how to respond to impacts from prescribed fires, then we're talking about the sub-kilometer range. And actually, let me go back to some data here. And you'll trust this is just from being in the field and just spending a lot of time looking at the atmosphere. But when we look at the concentrations and pollutions, what you see is, after the sunset, pollution starts to get really bad, and then it improves. And my conjecture, I'm calling it conjecture, the reason why I began to prove was, about 4 or 5 in the morning, the winds picked up. So that began to dilute the air. And also doing lots of early flight measurements and looking at the data, something that happens is that right before sunrise, the winds tend to go still. And that's when you see, again, the spike, because what happens is low winds means that there's not much dispersion. So things are concentrating, right? So, we're talking about at a scale of about 3 to 4 kilometers, really. But if we can, when the winds are weak, they're going to change very fast. So understanding what the winds are doing at a scale of sub-kilometer would be really important for this particular, when looking at this particular scenario of trying to assess what is the impact of particulate matter early in the morning.
You had a question? There's a microphone.
Yeah. So yeah, very interesting topic, and I think my question kind of is related to one you brought up already. Is just basically how do you scale the use of drones going forward? Because right now it does require a human operator.
Yeah.
So I found it fascinating when you talked about the delivery.
Yeah.
Drones potentially
Right.
becoming, especially if even without a sensor on there, they still act as a sensor.
Yeah,
with
exactly.
regards to the wind.
Right.
And then in coordination with the ground sensors, you could probably extrapolate data as well based upon those two pieces of.
Yeah, exactly. So low-cost sensors are becoming smaller and smaller and smaller. That was the sensor that you see on the table, the blue one. You're welcome to see it after the talk. Yeah. The other one, the blue one, Julius, I don't know if it or any, yeah. So that was their first iteration. Julius, can you describe what's the size of the current? So I think it's just a couple centimeters big, right? So it's quite smaller. So the sensing technology is getting smaller and smaller, and so we're quickly going to get to the point where it's going to be really easy to mount a sensor that measures particulate matter on a sensor. So if you can combine wind with particulate matter, you really are going to have this capability to not only understand how wind fields are changing, but also how these other tracers, concentrations of these other tracers are changing in the atmosphere. But one of the things that we've been dreaming about, and we've been talking with other collaborators, is about developing housings, intelligent housings that house the drones. And so the housing itself can look at weather and make a decision whether it releases the drone or not, right? And so if the housing senses that there is no rain, we can tolerate the winds, we release the drone, we collect the data, we come down, we downlink the data, and then we charge the drone. And we do this autonomously.
Yeah.
If we have Waymo, we can do this with right? It's just more getting the interest, to do that, the support to do that, and it's very much possible.
So you might deploy those across a strawberry field.
Yes, exactly.
And the thing would figure out when it should go up and come down.
When it goes up and when it goes down.
It becomes a vertical sensor.
Yeah. And we already know, based on the data, that things are most transient during sunrise and during sunset. So that's when we want to do the most profiling, so we can understand what's happening on a short time scale. In the middle of the afternoon, there isn't much change. You see sort of the same thing for about 4 to 5 hours. And then that depends whether you're winter or summertime. But we can definitely already know which are the periods. And in fact, when you talk to a modeler will tell you, we have great models that can forecast weather during the daytime, not during very early in the morning, and not during sunset, because that's when things are changing the most. And then the measurements that we have right now are not at the spatial and temporal scale that can help improve our models. So
one of the things that I've heard you talk about is the fact that there's this this unfortunate correlation is the wrong word, but the relationship between heat and pollution.
Yeah.
And the effects of heat on workers versus the effects of pollution on farm workers. Can you just talk about that a little bit?
And specifically, we've seen this in places like the Central Valley, and it happens also in the Pájaro Valley. But in the Central Valley, it gets really hot during summertime. And so what ends up happening is that because it's unbearable to work at around 2 to 3 p.m., folks start working at 4 a.m. to mitigate the heat stress impacts. But what we haven't realized is that we're taking them from that threat and we're putting them in the threat of higher pollution. So, because the measurements aren't there, and in fact, you can see it. I wish this was a laser pointer, but you can see that trend, right? So if you look at, let's look at what's happening here. And maybe I can use my pointer so that the folks online can also see this. But can everyone see my pointer? So look at what's happening here. So this is sunrise. It's about here, right? So it gets hot, and then after we reach highest temperature during the day, right? Then you see pollution go up, right? And then it begins to drop off. And we're still missing data. We have to look at the wind data, but I think what happened, there were some winds that were helping with the dispersion of the smoke. And then as things got still, pollutions went back up. And then once it reached the maximum concentration, and it only took about 1 or 2 hours for it to go back way below any risk area. And that's because what happens is during the day, we get energy from the sun. That energy heats up the floor. The ground absorbs some of that energy, and some of that energy gets sent back to the atmosphere, and so that creates turbulence. And so the more turbulence you have, the more dispersion you have. So it doesn't mean that you have less pollution in the atmosphere, but it means that you have lower concentrations at the surface. So the pollution gets mixed well up into the atmosphere. So if you look at, let's see if we can navigate back. This picture here is during the day, so you can see the layer. Hopefully you can see the layer.
Very faint.
It's very faint, but let me draw it so this is the layer of pollution that you see here. So that's during daytime, right? And what we've noticed is that this layer comes down when it cools down. So even if there isn't a fire, and this is why this matters, if there isn't a fire, the baseline is already quite bad, and that baseline that gets worse if it's cool, and it gets better if it's warm. So efforts to mitigate heat stress have people working earlier when it's cooler, and so that means there's more pollution near the surface.
So as long as we're on this picture.
Yeah.
As long as we were on that picture, you pointed out the students who were working on this project. These are undergraduate students, and this is kind of the epitome of experiential learning, right?
Yeah.
So can you talk a little bit about the backgrounds of the students who came to this project and what they may have brought to the project?
Yeah. So one of the things that I've done. So one of the things that I'm really excited at UCSC is that we have a very talented students from electrical engineering, computer scientists, electrical computer engineering, all things which I need. So very quickly started to work with them and learn from them. So most of our students, while many of our students come to us as early as while they're in the sophomore year, the students were excited about getting engaged in an impactful project for their capstone. So that to me was a unique opportunity because it's when they have the most. They've learned so much. They now spent 4 or 5 years at UCSC, and they're so excited to apply it to something. And so it was a very beautiful project where the students were just ready to hit the ground running and make a big difference. And very quickly, they knew very little about drones, but that's where I was happy to step in and teach them that. So as long as they were willing to share with me everything they knew about electrical engineering and computer science and computer engineering.
Yeah, I guess we didn't mention you're in the applied mathematics
the applied
department.
mathematics department, right? And hopefully I've demonstrated that we're putting mathematics to good use, but it's also the other engineering, right? And so bringing these are very interdisciplinary research.
That's one of the things I really appreciate about the engineering school we have, which is that it's extremely porous. Most engineering schools, you'll see very separate departments with very separate cultures in different buildings. Whereas in our engineering school, people are working across these traditional boundaries to just solve problems, which is great. So we have a question again from our Zoom listeners.
So from our Zoom listeners, they ask they're wondering if disease demographics support the idea that there are aerosols creating problems in the Watsonville community.
I don't have an answer for that. That's outside of my expertise. But I think this is where it's been interesting. If we've been exploring, so the answer is I don't have an answer. But I think this is where we can expand this work to collaborate, folks in the public health arena and with other scientists to apply this framework and get higher resolution data so that they can help us reach these conclusions.
Yeah. Question?
Yes.
Hold on. Could you wait
Yeah.
for the microphone? Here it comes.
Thank you. Two questions, kind of on the opposite ends of the
Yeah.
spectrum. First, I heard about the strawberry farmers,
Yeah.
and it seems like they may have incentives to cooperate with you.
Yeah.
But if you look at the dairy industry, unless they're driven by regulations, it's not clear that they're incented to work with you. Could you comment on that? And the second,
Yeah, go ahead.
the second question, sorry, this digs into the math, whether you, not saying whether you did it right or wrong, but you had a mass transfer or a mass balance with a mass transfer coefficient embedded in that.
Yeah.
Did you determine that from, say, your velocity data independently, or did you use that as a fitting factor for your concentration profiles?
That's an excellent question. So starting with the second one, we used that for fitting. So we used some empirical model. So we're basically using the data that we're collecting from the drone, both the concentration profiles and the vertical profiles, to fit the model.
Okay.
Yeah,
Thank you.
and that's how we go from the measurement to the emission. Excellent question. Thank you. And then the question about cooperation. I mean, I'm not just going to say, well, I'm just the sensor guy, but just sort of, I am a human there, and I make observations while I'm doing some work. But I feel like this has been very analogous to the deployment of solar panels, to where solar panel technology at the beginning, when this technology came out, I feel like there was some hesitation, right? Because it was like there was this uncertainty, I don't want to overuse this word, but they didn't know if there was going to be a return on the technology. And I think the same thing happened with these digesters. But since they began to be deployed, I only seen the number increase ever more rapidly. So to me, that tells me that folks are buying into the technology. And I think that's because of culture between farmers, so they talk to each other. So all it takes is just a critical mass of farmers to adopt the technology. Other farmers begin to see that they've received the return, and then they'll adopt it. So I think things are trending in the right direction. It's just we just have to be very systematic to make sure that these systems accomplish their end goal, which is to reduce emissions. But overall, I see, because the farmers that have had lots of success with these systems, they're basically taking the methane and they're using that as renewable energy to offset the cost from, for example, electricity. So they generate their own electricity rather than buying from utility. So all of a sudden, poop that would just disintegrate and contaminate, the planet, now it has a greater purpose, and it's reducing their overall carbon footprint. But there's still a lot more to do in this space. But things seem to be trending, from what I've seen, the adaptation, at least of the technology, I think it's increasing.
Could I, if I could ask just one more question? Completely different sort of topic, but we're hearing in the news a lot about fear of the technology of the drone technology becoming unavailable in the U.S. because so much of it is produced in China, and there's an attempt to limit what technology can come from China. How are you thinking about that with respect to your own use of the drone technology?
Yeah, I mean, so far we've been able to attenuate that with this great thing called startup funds. But if you're working on a research, on federally funded research, you can't use any technology that's coming from China specifically. So that presents a big hurdle. And so that would set us up some years behind.
Are you thinking about developing your own drone technology?
Yeah. So we're working on developing our own technology, right? We're forced to. So yeah.
Great.
Well, thank you very much, Alex and Javier, for
thank you.
fascinating conversation. Thank you all for coming tonight. Please join us for Please join us for our next lecture on February 4th, where we'll have biology professor Rachel Meyer will be talking on learning about Earth's biodiversity via space and eDNA. Good night, everyone.
Thank you so much.
Thank you.